just to kick off, and again, I'll run through these relatively quickly. I'll try not and spend too much time, since I think most people are familiar broadly with the project, and then that gives us a bit more time for some discussion, since for some of us it's the first time from a Cranfield perspective that kind of all the relevant people have been perhaps together on one call. So looking at this first slide, obviously it's titled towards a European lunar materials handling and geotechnics payload, and that's in the context of an anticipated future lunar surface economy. So I'll kind of introduce it and explain that, and also this new term and Project Mule, which is a term that's come out of a project that's complementary to the first project I want to talk about. And that second project is being run as part of our Cranfield MSc course. And as you'll see, Project Mule stands for materials utilization in a lunar environment, or lunar economy rather. And you can see in the top corner there a logo that group's put together. And so the contributors to this, myself, the members of an ESA study that we're running at the moment, plus members of the Cranfield MSc course, National Space Engineering, plus 2 research students, which I'll mention as we go through. So the idea, and I apologise, some of these slides are slightly wordy, but this just gives you a rough breakdown of what I'm going to talk about. First of all, overview what we mean and what we think a future or near future lunar surface economy is going to be. Secondly, highlight within that the upcoming importance of bulk materials handling, which is really the focus of this presentation. By bulk materials, that's a term used commonly in industry on Earth, and what we really mean is handling primarily fine or granular dried materials. Thirdly, then outline an argument for a proposed knowledge gap that we think exists in terms of materials handling on the lunar surface. Indicate what that resultant knowledge gap means in terms of what the issues in terms of that knowledge gap, and then argue the need for an early hardware or payload implementation on the lunar surface to help narrow or close that gap. So that really builds up the case for what we're doing, and then we will start looking at where we are in terms of a proposed solution, which is one or more payloads to go onto the lunar surface, what they are, how they would potentially operate, what they would do to try and close that knowledge gap. And then this last batch of items here is very much to try and give you a flavour of the current work, where we are with projects which are very much ongoing and certainly not yet complete. The original title for the project included the words geotechnics in it, so materials handling and geotechnics on the lunar surface. We've ended up de-emphasising the geotechnics and see that as something which we will pursue in the future. And so what you're going to hear about today is primarily bulk materials handling. Geotechnics, it will be for a future activity. So this all came about through SONet. So it's very pertinent to kind of be talking about this within the SONet context. So the original idea which spawned all of these activities came from an original idea or original concept that was initiated in a discussion within a SONet meeting in late 2019. So kind of just around about 2 years ago. So SONet was really, or the discussion that came out of the various people who were in that meeting, actually initiated this. So therefore, what we did to take that forward, we then put together a relevant team of experts and members, which really broke down into two areas. First of all, people who came from the SONet network, and then secondly, additional people I brought in with my knowledge of the UK relevant lunar communities. And what we did was then put together a proposal that we submitted to ESA, And after a couple of rounds of more detailed proposals, that then resulted in a funded one-year study that started early last year and finishes in, well, it says April 2020. That should be April 21 and finishes March, April 2022. And so that'd be the first bit of the talk, is to focus on that, and then towards the end focus more on some of the other projects and other activities that have now been initiated that are complementary to this ESA supported study. And here this just gives you a kind of list of the kind of members involved, and these are very much an expert group who are helping to guide and comment on the work that we do primarily at Cranfield. So very much an advisory group, and I won't go through all the names, but a combination of people with a lunar science background, a space systems background, and a mining geotechnics background, materials handling background. So we've got a nice balance of the different expertises we see relevant, and coming from a variety of different sources, some from SONET, some from the UK, and also representing across primarily Europe, but also somebody from Australia as well. So a reasonably diverse group of people. And so that project, what was the basis for that project? So the first bit is to kind of consider the argument about what a future lunar surface economy will be, and the potential knowledge gap that we think exists. So if we go through these one by one, I won't spend too much time because hopefully most of the people here understand kind of this context. So clearly one context is we know that humankind is going back to the moon with the intention of having a persistent presence on the moon and in deep space. So not only the moon, but also onto Mars as well. So obviously that gives a very different context than say a few years ago where there wasn't a clear plan to get humans back beyond low Earth orbit onto the moon, onto Mars. Again, well established now within the community is the need for a sustainable approach to do that. And what that really means is we can't afford to take everything out of the Earth's gravity well to support those activities beyond low Earth orbit on the moon and Mars, and therefore the need to look to exploit locally found resources, so what the community calls in situ resource utilisation. It's a common theme. And on the lunar surface, what this means is proposing to extract surface and near subsurface mineral and frozen volatile resources to provide a whole range of potential products. So that includes oxygen, metals, and minerals themselves for construction. And those activities are viewed more and more to have a commercial arm to them, so not simply supported by national agencies, but also much more of a public-private kind of activity going forward. So therefore starting to think about this not as just simply a technical challenge, but also as a potential economic opportunity. So very much emerging idea of a future lunar surface economy, with the first marketable product likely to come out of that being the provision of oxygen, either extracted from volatiles or from minerals, that could then be used as a propellant for chemical rockets. And if we look at what people are doing within this, so if we accept this is well established within a large part of the kind of space community as a reasonable vision going forwards, what we see is that the community is focusing quite strongly on thinking about specific implementations to exploit this, so specific approaches to mining, to extraction of minerals, to processing them for construction and manufacturing. So very much focusing on specific implementations. And our realization is that underpinning all of that activity is that the excavation, the processing, construction, manufacturing will often involve handling of bulk materials, or bulk materials as we call them on Earth, so granular, fine granular, pounded materials, handling those materials on the lunar surface in the lunar environment. So something that underpins all of those activities. And next part of the argument is what is the knowledge gap and the resultant risk that comes from that observation. So the first key point here is that whilst most groups, as I've already said, is focusing on early development of particular implementations, few groups are focusing on understanding the underpinning aspects of granular and powdered materials handling in that lunar environment. And therefore, we feel that there's an emerging knowledge gap. And if we think why do we think there's a knowledge gap? Well, on Earth, we know how to do all this stuff. We know how to handle bulk materials. We've been doing it for thousands of years. But the argument is we cannot simply transfer all of that knowledge directly to the lunar environment and the lunar materials we're going to be handling. And therefore, you can argue that that lunar environment is unique, very alien in terms of both the environment and materials. So in terms of the environment, we have a combination at the same time of reduced gravity, the lunar exosphere, in other words, a hard vacuum, high electrical charging due to continuous bombardment with the solar wind and deep UV from the sun, given the lack of atmosphere, and extreme temperature swings. So multiple environmental parameters which are very different than those found on the Earth, plus the lunar materials. Although the fundamental mineralogy may be the same as on Earth, actually on the lunar surface we end up with a vastly different material because it's produced by different methods. So we find typically the lunar regolith, which is a fine, granular, almost powdered material formed by micrometeoroid impact. And so property-wise, it's fine, highly angular, often different from most materials we find on Earth. The lack of wind and water processing on the lunar surface again maintains those highly angular particles. And also the surface physicochemistry of those particles again tends to be very different because of the continuous charging, the lack of an atmosphere, lack of water to change that surface chemistry, but also radiation processing. So both the environment and the materials, we argue, are very different than what we normally have to deal with on Earth. Plus, the other key point is the ability to simulate or replicate those environments and materials on the surface of the Earth is very limited. So it's really not practical to simulate all of those lunar environments simultaneously on Earth. Plus also, it's difficult to produce the same chemistry, the surface chemistry, the particle size features on Earth. So our regular simulants are also, we think, quite naive and not good replicas of what happens on the lunar surface. So therefore, that gives us a challenge. We can't easily replicate physically what happens on the lunar surface to try and understand it better. Plus also to try and simulate such things computationally in silico is also difficult from the point of view of none of those have been actually validated on the lunar surface. So although we can model, those models haven't been validated. And therefore, that's the argument to say there's a knowledge gap in terms of how lunar materials will behave, especially in the envisaged industrial, civil engineering, manufacturing processes on the lunar surface, which we see relevant to a lunar surface economy. And the last point, the risks, is that what that means is that as the Earth-based community develops or takes more and more resources to try and develop particular implementations, there's a risk that all of that resources being used at the moment to do designs and such is potentially being used quite inefficiently, because there's a high risk that those designs will either fail or certainly work non-optimally on the lunar surface when implemented, simply because they're being designed and tested without the ability to properly replicate what will happen on the lunar surface. So that's the argument in terms of the knowledge gap and what the resultant risk is. And so therefore, what we've proposed is that given this inability to generate the knowledge on Earth, what we need is a timely, and the key word here is timely, implementation of a dedicated lunar surface payload that's able to study, demonstrate, and de-risk or validate lunar surface materials handling to fill this knowledge gap and to de-risk, obviously, all of this kind of activity that's going on, and potentially doing that itself. If there's going to be a future lunar economy, getting that knowledge potentially has commercial value. So there's also potentially a commercial argument for generating this knowledge immediately, as opposed to simply kind of the future processes that could be implemented more efficiently with better knowledge. So more context why this seems to make sense. There's increasing availability and reduced costs, or reducing costs, to get payload onto the lunar surface. So we have the commercial kind of lunar surface delivery services being developed by the NASA CLIPS program, which offers more opportunities and cheaper way to get material on the surface. Plus also ESA is working on lunar logistics lander, or so-called lunar logistics lander, or large lunar logistics lander, which again is another potential mechanism to get payload onto the lunar surface. We've already argued about something about the pace of development, that if a significant Earth-based activity already starting and growing in this area of trying to develop processes with the lunar surface, we need to get this knowledge relatively quickly. If not, we run the risk of people flying and multiple people learning the same lessons of potential failure or inefficiency, and generating the resultant knowledge going forwards. So therefore, we need to generate this knowledge in a timely, early fashion, so that it can then be efficiently used by the community, rather than the community wasting their time all individually learning these lessons. Therefore, we feel that this needs to be implemented well before 2030, potentially by no later than 2027. And therefore, that will then start driving payload mission development. We have to use existing high TOL if we want to fly something within those timescales. And also, we'll have to try and avoid developing new technology, given those timescales and the TOL argument. Primarily look towards translating existing non-space technology into the space sector. So in other words, doing what in some communities is called horizontal innovation. And therefore, the Cranfield led this European team, elaborated this argument to ESA to then result in some funding to start exploring what a payload could look like. And so therefore, to give you a bit of a flavour of that, this is what the study broadly involves. So this is almost the programmatics of that. So it started in first quarter this year, finishes first quarter next year. And these are the key work packages. So to review existing knowledge that's relevant to the study, to develop a science and technical case, including a prioritised list of science and technical questions, to produce scientific and technical requirements for the mission and the payload, to consider payload concepts, and to select and refine a preliminary payload architecture, to produce a roadmap for future developments and implementations beyond the initial 12-month study, and to establish and grow a community able to then support, develop, and exploit that payload. And as you'll see, as we go forward, there's a number of other parallel studies that's emerged to go alongside this ESA-funded study. So this just captures some of the key emerging kind of objectives and requirements out of the early part of that ESA study. So the first one is to kind of really clarify the need for timely delivery. So to have initial knowledge generated by the middle of the second half of this decade, so around about 2027. For timely implementation, that then drives the payload solution. So it dictates that the payload's got to be compatible with existing or emerging lunar delivery systems, and also to adopt the fail fast approach. In other words, to assume that we don't just have a one-off opportunity, but rather we have multiple opportunities to fly, and therefore we can fly quickly. And as long as we make sure we can learn from the first payload, including failures, we can then feed those forward into a second iteration, which we fly again, and therefore rapidly develop understanding and knowledge about both the payload and obviously materials handling. Other objectives are to, or that's emerged, is for that payload to be obviously focused towards things that are relevant to a future lunar surface economy. So that's both in terms of materials and the locations in which we do the demonstrations. And another thing that's emerged is to focus primarily on practically demonstrating in situ materials handling concepts. In other words, focus towards real world applications, real world knowledge, and we'll come to what some of those features are, rather than focus on providing a more science-based kind of underpinning understanding. They're very much trying to rapidly develop practical knowledge rather than fundamental knowledge. And therefore looking to try and validate and refine materials handling, modeling and simulation tools in the process. And in terms of size scale, we're looking to identify and demonstrate processes at the payload stage at the size scale of tens to hundreds of grams of material per batch or per unit time going through these systems. But importantly, that we should ensure that what's ever demonstrated at these size scales is scalable, that knowledge is scalable to what we envisage being the size scales that's relevant to a full scale implementation. And what we assume that is going to be on the tens to hundreds of kilograms per batch or per kind of unit time going through this. Plus also the early work has clarified that we shouldn't be focusing on any specific ISRU or physical processes, rather we should be focusing on generic approaches. So the idea so far and what's emerged out of the ESA study is that what should be the key materials handling processes to be considered? It's really a string, you'll see this in the next slide, a string of different processes that we can envisage being commonly used in many different specific implementations of ISRU, manufacturing and construction. So that is excavating, getting materials off the lunar surface, internal transport or conveyancing, some form of physical size sorting of the materials, bulk materials handling in rotating systems, filling and emptying of static systems, something things like hoppers, looking at the electrostatic handling properties, looking at the ability to form what we'd call open piles of materials, and also what happens when we try and compress bulk materials. So again, very relatively simple, basic materials handling concepts. From the point of view of then the payload, if we're primarily driven by demonstrating these processes, we obviously need to have instrumentation to observe them and to measure them, and therefore to identify or to look to identify key instrumentation that allows remote capture. And that's to capture both the nominal, the expected performance, but importantly with the fail fast approach is to also be compatible with non-nominal performance, in other words, capturing failure modes, both what we'd call known unknowns, in other words, ways we can anticipate the system would fail, making sure we can capture that knowledge, but also being flexible enough that we can capture the unknown unknowns. In other words, being able to capture data that allows us to document and understand failure mechanisms which we never predicted would happen. It's all part of the fail fast mindset. To ensure that dust generation is captured and behavior is kind of understood. To also include, again, we're trying to use this to extract real world usable knowledge, to also extract, given we'll have mechanisms interacting with lunar regolith and materials, to understand and to extract information concerning general mechanical wear and failure, and so therefore addressing things like potential future understanding of maintenance of these full-scale systems. And as we've already said, looking at high TRL commercial off-the-shelf solutions which you can transfer across, and we're looking for this concept for kind of payloads that are in the less than 100 kilo, less than about a meter cubed volume. So what does that mean in terms of initial thoughts in terms of payload designs? So this is a schematic courtesy of the Cranfield Mule GDP, just to give you some flavour of those things which I've already just listed out. So what we have here is obviously just a kind of simple PowerPoint schematic, but showing sample acquisition in the form of the baseline choice of, at the moment, a bucket wheel, then internal conveyancing via, as you'll see in a couple of slides' time, screw conveyors, then size sorting in terms of sieving, rotating drums to observe dynamic handling, feeding into static hoppers that allows us to demonstrate filling and also then unloading of those static hoppers. Free fall through relevant or near relevant electrostatic plates to look at electrostatic effects, and then that free fall to look at pile formation, and then the ability to compress that pile and in fact inject it to waste to show compression methods. So we'll come back to this at the end into the potential discussion, because obviously one of the issues in terms of space systems engineering for this is potential single point failures, of which is a whole string in this kind of simple kind of schematic. So looking at all of these in slightly more detail, so these are again slides taken from a recent presentation from the kind of from the Cranfield MSc project, which I'll come to in a short while and describe in a bit more detail. So process one will be sample acquisition. So again, I won't go through these in great detail, but looking to utilise an approach that's already being considered commonly for many lunar surface applications. So bucket wheels as a way of acquiring samples. In terms of conveyancing, looking at screw conveyors, again, well established in terrestrial applications, and as part of expanding the community that's working on this, we're bringing in a number of commercial providers, in this case a company called SpiroFlow, who design and provide this equipment for terrestrial application, but also this is already being considered by a number of groups for space and lunar applications. So for example, NASA's got some programs looking at screw conveyors, planetary applications. Size sorting via sieving, and again we've chosen and working now with a company that has been involved in some relevant planetary studies using parabolic flight to demonstrate some of this technology under simulated lunar gravity conditions. So again, looking at taking technologies which are already starting to be considered relevant to a lunar economy, but also well studied and routine in Earth applications. Rotating drums, and therefore this is from a study from Technical University of Delft that has again flown a parabolic flight under lunar gravity conditions, looking at the dynamic handling of granular material in rotating drums. Remember, rotating drums is a common feature of many industrial processes which you can envisage on the lunar surface. So again, a common feature. Static hoppers, again, well established on Earth, and again, these kind of features will need on lunar surface to kind of store materials at various stages of kind of real lunar industrial kind of processes. Electrostatic, so remember on the lunar surface, electrostatics are likely to be much more dominant in terms of a kind of phenomena that affects materials handling compared to on the Earth's surface, given the inability to easily dissipate charge on the lunar surface and the fact that materials exposed to the lunar environment can become quickly charged because of the direct interaction with the solar wind and solar UV. Pile formation, again, can be expected to be a common process. Usable materials handling knowledge can be obtained from simply observing pile shape and pile formation. And the last aspect is compression. Again, an important common feature is to understand what happens when bulk materials are compressed. Therefore, this is a feature we are expecting to include. And one aspect of compression, in addition, or some aspects of compression, in addition to simply looking at the mechanical features, is that compression can also be used as part of a processing step as well. So two aspects we're considering in a bit more detail. One is potentially the ability to demonstrate, at least symbolically, some kind of manufacturing process, so compression potentially with a kind of a binder material that could result in monolith kind of structures being created. The other aspect of this is that if we are going to have any dried material we bring from Earth in terms of, for example, a binder to add to these materials, we also could bring with us Earth regolith, on-site Earth lunar regolith simulant. And one of the kind of arguments for this is that we want to understand whether the regolith simulants we use on Earth are good simulants of lunar materials. And one way to do that, if we have the ability, is to fly those simulants from Earth to the lunar surface and then demonstrate their behavior on the lunar surface. And if we can demonstrate that they do behave like lunar materials, fantastic. We have validation of that, and therefore we can use those lunar simulants with increased confidence. Clearly, if they don't, then we've got evidence that those simulants aren't appropriate for kind of the Earth-based studies that are even now ongoing with those regolith simulants. One last point here is the instrumentation. And so the focus we're having here is, again, thinking about pragmatic solutions that are a kind of compromise of simplicity to integrate into space systems, but also relevance to future full-scale implementation, so demonstrated implementation which we think would be needed anyway as part of a full-scale lunar system, simply for good process control, but also able to extract rich kind of information and deal with what I've mentioned previously, is also dealing with the unknown unknowns. In other words, to be able to capture failures via mechanisms which we didn't anticipate. And so the approach here is to primarily use imaging techniques. So machine vision as a way to observe a large part of the kind of the behavior of kind of materials and processes. Thermal imaging, so that when temperature is important, we can easily kind of obtain thermal information, again by methods which are relatively simple to integrate within a system. And also hyperspectral imaging, given that we'll need to have some knowledge of what the materials are we're feeding into these payloads, in terms of the mineralogy. And again, hyperspectral imaging is already being used for routine process control in Earth applications. So again, very well matured technology which we can look to transfer across to lunar use. So again, hopefully solutions that address our requirements of ultimately allowing us both flexibility, ease and rapid integration and potentially flight to the lunar surface. So again, just a few more images here. The key ones here perhaps are to focus on this image here. So this is just a CAD image representing the payload volume of one of the existing lunar landers. This is the Astrobartic Peregrine lander that is a potential option to commercially fly a payload onto the lunar surface. And so this just shows with a mannequin the kind of size scale that could be used, although obviously there are issues to do with the kind of actual cost of delivering such a large payload to the lunar surface. But we'll come back to that in a short while. So that was to summarize some of the kind of outputs of the ESA study. What I want to do now for a few minutes is to talk about a couple of other projects that's emerged off the back of, or now running parallel to, the ESA study that complements the ESA study. So this is Project Mule. So Mule, remember, stands for Materials Utilization for Lunar Economy. And the team here is 15 students who are on our current Cranfield MSc course in Astronautics and Space Engineering, which for this academic year is about 90 students on that course. And as part of that course, groups of around 15 students each perform 6-month part-time studies, what we call the group design project. Part-time group design studies from October of this year through to March of next year. Part-time because they have lectures and other activities within the course going on at the same time. And one of the teams, and there's a number of members of the audience from this team, was allocated to Project Mule. And the idea or the objective of Project Mule is to consider a mission program able to fly and operate the proposed materials handling payload on the lunar surface. So hopefully it's obvious now how they're complementary. So the ESA study is focusing primarily on the payload, whereas the Mule project is focusing primarily on the ways to get the payload onto the lunar surface and to operate it. So hence it's complementary. What are the initial thoughts that's coming out of that study so far? Well, first of all, with that group has realised, given the context that the payloads generated, is to consider a program. In other words, not a single flight, but a program of flights. In other words, a number of individual flights or missions, and to consider initially the first 2 flights of a program. So remember, we've talked about before the idea of fail fast. So the idea of having the ability to fly the payload more than once, so we can rapidly learn from the first payload and refine it for the second flight. So that first payload has we're looking, or the group is looking to have that flown no later than 2027 to minimise risk within that first payload, and therefore that will be a static payload on obviously a static lander with the ability to only sample a few meters, in other words, with some kind of arm, in this case with a bucket wheel, on that static lander. So the ability to kind of only sample from a very small area on the lunar surface, literally kind of almost underneath the lander, which has a number of issues as well. And that first flight, again to de-risk, is proposed to a site where there's already in situ ground truth on materials handling. In other words, somewhere where humanity has already visited and got some knowledge of how that material will behave. So, for example, the Apollo sites. The second flight is going to go to a site which will be directly relevant to a future lunar surface economy. In other words, most likely lunar South Pole. The second flight, as we've already said, will have lessons learned from the first flight, so feed forward lessons learned from that first flight into the payload, but the payload will be primarily the same. And the second flight will have the ability to have a wider variety of materials to be able to sample from up to 1 kilometre from the landing site. And the pragmatic solution to do that is to still have a static lander on a static payload on the static lander, but to have a small commercial fetch rover to collect samples from a much wider area and bring them back to the payload. One reason for that is there is emerging, in this case again astrobotic, the idea of having commercial small rovers being available that could be then used. So just to round off, to give us a few minutes for discussion, so that GDP, that Cranfield MSc project, looking at the missional program, so that is just finished its first kind of major review of activities, and obviously will then continue working through until kind of mid-March of next year, and will look to deliver a baseline program that could deliver the ESA payload, and also, of course, capture kind of lessons learned from that design process, for that mission design, program design process, that which we then feed forward into kind of future phases. One of the aspects of that payload, or the route that payload's taken, is the idea of using quite a large payload. And so there are still some uncertainties as to whether that actually is viable in terms of the actual cost of flying that payload. And so we've got another program which we've just started with a new kind of PhD student, which is to look at some alternatives to that large payload, the idea of small CubeSat-sized payloads or CubeSat-compatible payloads that could go onto the lunar surface, hosted on one of these landers, but now only having a few kilos rather than up to 100 kilos. So something which is financially potentially much cheaper to go to the lunar surface to still demonstrate in situ kind of materials handling and to de-risk that. So the key issues here is that to have the possibility of something being more realistic in terms of mass and financial cost, as I've said, only a few kilos, but of course with the pragmatic kind of constraints of having a limited ability to demonstrate materials handling, potentially only one or perhaps at most two processes, and also having to deal with the risk, or this point in time, the uncertainty as to whether something that is even smaller than our large payload, which will only likely be demonstrating materials handling on the few grams, let alone a few tens or hundreds of grams scale, whether that can generate knowledge that will be usable and scalable to a full-scale implementation at the tens to hundreds of kilogram scales. That's just to quickly kind of capture a project that's just started, but is highlighting another strand in terms of kind of thought processes, in terms of trying to generate some knowledge about lunar materials handling. So in summary, what I've hopefully done is to give a context of a near future lunar surface economy, highlighted what I think, or what we think is the upcoming importance of bulk materials handling on the lunar surface, outlined an argument for a knowledge gap concerning bulk materials handling and the risks that that creates, argued the need for a payload that goes to the lunar surface given our inability to replicate all of the features necessary to get the information on Earth, outlined the idea of the need for payloads to go to the lunar surface to generate this knowledge, and then given a flavour of the activities that's emerged to then try and start working towards that. So the ESA study, the Cranfield GDP, and the kind of the small CubeSat compatible study. So with that, I will stop. Apart from the last slide, which is almost that self-critique of saying, well, given all of that, what are some of the kind of questions that perhaps could be asked? One is, do we really need rapid implementation? Is it feasible to get something on the lunar surface to start the knowledge generation by 2027? Financial costs for the payload, is it really realistic to get these relatively large payloads on the lunar surface, and especially to have more than one, given the multiple flights? And is this fail-fast philosophy also a sensible route to take? Also, with our large payload, are there too many single point failures? And given that our chosen processes to implement, we still do need to have some anticipation of what the behavior will be on the lunar surface, so we can appropriately modify them to minimize the risk that those processes will fail from the very outset when we in our first implementation. So with that, I'll stop and hopefully answer any questions that the audience has got, or start discussing and debating some of these points.